Welcome dear students, welcome to my channel. Today we will discuss about dampered simple harmonic oscillations. Before discussing dampered simple harmonic oscillations, we will talk about what we have learned so far. In all the previous lectures, we have learned about the simple harmonic motion of different systems. For example, spring mass system, a simple pendulum, a rod. For example, we talked about the spring mass system. In spring mass system, if I disturb this spring mass system by applying some external force and I leave it, it will start oscillating freely. For example, here I compress the spring. I'm compressing the spring and I will let it go. It will start moving up and down about its main position, and we have checked that this motion is simple harmonic motion, and we have derived the equation of motion for simple harmonic motion, and we have derived for the displacement, for the angular frequency, for the time period, and the energy. If you notice that once you displace this spring mass system, it is executing simple harmonic motion by itself. Alright, if you check on the screen, the amplitude of the oscillations is not changing. Alright, that means the amplitude remains constant, and hence the energy that I provided to it remains in it forever. Alright, and you see the amplitude is maximum amplitude is constant in each oscillations, and its frequency is constant, and its time period is constant. Its time period is called free time period, and the frequency is called natural frequency, and the frequency of the system is under root of k or m. K is a spring constant, and a mass is the mass attached to this spring. Alright, this is an
oscillation is free
system.
oscillation.
In reality, this is not true. In reality, you see, once you disturb this spring mass system, in time it is losing energy and continuously, and its amplitude is decreasing, and ultimately the body comes to rest. In reality, we have damping forces. Whenever a body is in motion, there are some forces called damping forces which try to bring the body to rest. These damping forces are, for example, frictional forces or viscous drag. These forces lead to decrease in the energy, and hence decrease in the amplitude. For example, if I take the spring mass system, and in reality what happens if I am disturbing it, its amplitude is decreasing. Although this is periodic motion, but its amplitude is decreasing, and hence its kinetic and potential energy is also decreasing. Alright, such oscillations are called dampened oscillations. Alright, because some external forces are acting on the system and the body comes to rest. We will now discuss about the equation of motion of damping oscillations. Differential equation of a dampened simple harmonic motion. We consider a spring mass system and attach it rigidly to a fixed spot, and a mass M attached to the lower end. A disc is attached to the lower side of the body and is immersed in the liquid which is contained in this beaker. When the mass is pulled down and let free, it begins to oscillate up and down along with the disc. When the disc moves up and down in liquid, a viscous drag acts on it and also on the mass system. Okay, the various forces will act on the system. The forces are restoring force and frictional force. Okay, while it is oscillating in this liquid. Let's write these.
Number first force will be the restoring force. When it is oscillating, this restoring force will oppose the motion. Okay, where K is the spring constant and X is the stretch produced in the spring. Okay. Another force is the frictional force, which is proportional to velocity. Okay, if you see, when it is moving faster with a high velocity, the more viscous drag or opposing force will act on the disc and hence on the system. So this frictional force or the viscous drag is proportional to velocity, or it can be written as b over v, or it can be written as minus b x dot, where b, this is a constant and is known as damping constant. Damping constant. Alright, and it depends upon the nature of liquid. Alright, and x dot is the velocity. So these are the two forces acting on the spring system, and both are having negative sign. This negative sign shows that frictional force and this restoring force are opposing the motion of this system. Okay, net force will be F1 plus F2. Okay, so net force is minus kx. All right, restoring force and this force, so this frictional force. Okay, it can be written as, when it oscillates, it has suppose acceleration a, and so the mass into acceleration force is mx double dot. So mx double dot will be equal to minus kx minus bx dot. We can write it as x double dot plus bm x dot plus k by mx is equal to 0. So this is the second order differential equation for damped simple harmonic motion. And now you see, if x dot is 0, then x double dot plus k over m x will be equal to 0. So this is free or undamped oscillation. Undamped oscillation. Okay, and you see that omega is under root k over m, and time period is 2 pi under root of m over k, and the solution is a cos of omega t plus phi. Alright, this omega is omega 0. This is known as natural frequency. Alright, this is the solution of the free oscillation. But let's check the solution of the damped simple harmonic motion. The graph of the free or undamped simple harmonic oscillation is like this. So it is a sine graph, or it can be a cosine graph, and you see the amplitude does not change with time. The graph of the free or undamped simple harmonic oscillation is like this. So it is a sine graph, or it can be a cosine graph, and you see the amplitude does not change with time. Okay. So damped simple harmonic motion differential equation solution. This is the solution of this differential equation. And here you see this x e raised to power minus lambda over t is the amplitude of the damped oscillations, and this omega b is the frequency of the damped oscillations, and this lambda is b over 2m. And you see this amplitude is decreasing exponentially with time. Okay, and you see here the amplitude goes on decreasing with time. Okay, so it decreases exponentially. Now the angular frequency of this damped oscillation is under root of k over m minus b square over 4m square. Alright, now again, if you see that b is 0, this will be under root k by m for free oscillations. Okay, and the time period of the damped oscillation will be 2 pi under root of wb. So time period will be 2 pi, it will be under root of k over m minus b square over 4m square. Alright,